He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
Kia ora and a very big welcome to Elemental from RNZ. This is episode 96 and it is... Gulp. The final episode of the series, in which, of course, we've been celebrating the 150 years since Dmitri Mendeleev published the first iteration of the periodic table. I'm Alison Ballance.
And I'm Allan Blackman from the Auckland University of Technology. And I know we have covered all 118 elements on the periodic table, and here we are at the final one. I know, again. And this is our second element that starts with the letter Z, zirconium. And it's a tale of a shape-shifting tough cookie that spans gemstones, medical implants, and nuclear reactors. Not that it's radioactive itself.
In honour of this being a bit of an end of an era, I thought I should do some zirconium homework of my own, so I'll add time capsule to that list, but we'll get to that. Now, I'm familiar with zircons, which are very pretty gemstones, and coincidentally, since this is December, but completely unscientifically, of course, blue zircon is apparently the birthstone for December.
Indeed. So, zircon is a mineral. It's actually zirconium silicate, and it's the most important source of the element zirconium. We'll come back to gemstones in a minute, but first, as per usual, and for the final time, the vital statistics. Elemental symbol of zirconium ZR, and the atomic number 40, and that puts it in the transition metals. So, where did it get its name? Zirconium comes from the Syriac. And that was new to me, but it was a language spoken in ancient Syria. Surprise, surprise. So it comes from the Syriac zargon, meaning the colour of gold. And that's kind of an unusual name for a metal that looks like, well, pretty much every other metal on the periodic table, silver-coloured. As we said, its main source is from gemstones that contain zirconium, namely the zircons that we've already mentioned, and they're also known as jargon, which is a corruption of zargon, or indeed hyacinth, or jacinth, or ligure, and these are all mentioned in biblical writings.
So we've known about zircons for a long time then, but when did we find out about the element?
Okay. So the new element zirconium was identified in 1789 by Klaproth, he of uranium fame. And ironically, a bit of a dogleg here, zirconium was found to be an ideal material when alloyed with tin for use in nuclear reactors because A, it didn't corrode, even at high temperatures, and B, it didn't absorb neutrons to give radioactive isotopes. So, seemingly ideal. Unfortunately, if it gets too hot, though, over around about 900 degrees Celsius, it reacts with water to form hydrogen gas, which is something that you really don't want in a nuclear facility. And sadly, this is what happened in explosions at both 3 Mile Island and Fukushima. So, back to discovering the element, the metal itself was first isolated by Berzelius, that famous Swede. And remember, he discovered a few elements in his time. See, for example, cerium, selenium, silicon, and thorium. But he only found it as an impure powder, and it took another 100 or so years before the pure metal was obtained.
Oh, that's sounding almost as tortuous and time-consuming as a lanthanoid.
Indeed.
So once we finally found zirconium, the metal, what did we start doing with it?
So like its upper neighbour on the periodic table, titanium, zirconium metal is biocompatible and therefore used inside the body in surgical implants. The metal itself is relatively high melting, and it's been used in spacecraft that have to re-enter the Earth's atmosphere. And the very thin oxide layer on zirconium metal makes it extremely resistant to both acids and bases, and therefore it finds use in applications involving corrosive species.
Now, as a biologist, I know of things like endangered species and invasive species. Could you just sort of unravel that a little for us?
Corrosive species. So, yeah, basically anything that has got a decent acid content or a base content. They can both be corrosive. And generally, obviously, what happens often with metals is that you put them in an acidic or a basic environment, they will certainly corrode. They'll end up rusting, oxidizing, call it what you will. But zirconium, really, really, really resistant to those sorts of things.
Now, where would most of us come across zirconium in our day-to-day lives?
Well, indeed, it's probably going to be in jewellery. So the oxide of zirconium, which has the chemical formula ZrO2, is the zirconium compound of which many of the general public would have heard, zirconium dioxide or zirconia. Now, we know cubic zirconia as fake diamond, and it's worth a little discussion, if only to answer the question, why is it called cubic zirconia? And this has to do with the way that the zirconium and the oxygen atoms are arranged in cubic zirconia. So the structure of the bulk material is based on a tiny, 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 believe me, cube of zirconium and oxygen atoms. And this tiny little cube gets translated in 3 dimensions to form the whole zirconia structure. Now, cubic zirconia is one of 3 forms of zirconia. The other 2 are called monoclinic zirconia and tetragonal zirconia, with those names again referring to the arrangement of the zirconium and the oxygen atoms. And interestingly, the cubic form is only stable at high temperatures. And that's, when I say high temperatures, I mean around about sort of 2,300 degrees Celsius. So that's going to be no good at all, because when you cool this stuff down, it's just going to revert to its more stable phases. So for use in gemstones, what we do is we dope the zirconia with yttrium oxide from our second last episode. And other compounds can also be added to give colour. Now, zirconia is nearly as hard as diamond and has nearly the refractive index of diamond. And just for those of you who don't know, refractive index is a measure of the speed at which light travels through a material. And zirconia has actually a greater dispersion than diamond, and that means that it splits white light up into its constituent rainbow colours. And as a result of the latter, zirconia sparkles just like diamond. But sadly, it's viewed as a cheap and nasty alternative to diamond, when really it should be admired for its inherent beauty, I reckon anyway.
Cheaper too.
Yes, indeed. That's the problem. So more than just decoration, zirconia is what we call a refractory material, meaning that it is pretty much impervious to both heat and pressure, amongst other things. And it therefore finds use in ceramics and abrasives. And indeed, you can take red-hot zirconia ceramics and drop them into water and they won't crack on you, which is pretty incredible.
Cool. Although that seems like the wrong adjective to describe something very hot. Never mind. Here's my interesting fact. So going from zirconia, fake jewellery, to the real-life thing, the zircons. Zircons are also really tough, which makes them really useful in dating old rocks. So the zircons are these tiny time capsules, and they've got trace amounts of uranium and thorium, and from that, geologists can work out how old they are. And it turns out that zircons are almost indestructible. No matter what you do to them geologically, they can withstand immense pressure and heat, and they just stay looking like little zircons. So there are some zircons from Western Australia that have been dated back to more than, wait for it, 4.4 billion years.
Ooh, that's nearly the age of the Earth. That's incredible.
I know, just think of it. A little crystal that was formed all that time ago, and it survived everything that's happened since. Okay, what's your closing interesting fact?
Well, that's going to be a hard one to beat, that I reckon. So we mentioned zirconium as a shapeshifter. So the compound lead zirconate titanate is a ceramic that shows a marked piezoelectric effect. And that means that the compound actually changes shape when an electric field is applied.
Oh, excellent.
And also the opposite. When you pressurise it, you get electricity out of it, so which is pretty incredible.
That's even better.
So zirconium tungstate has the unusual property, the really unusual property, of shrinking in all dimensions when it's heated. And that's sort of contrary to our reality, I guess, whereas We expect pretty much if you heat something, they're going to expand. Zirconium tungstate goes the other way. So this is called negative thermal expansion.
Well, it occurs to me that this is the complete opposite, negative thermal expansion that is, of our podcast series, which has expanded in more directions than we realised it would when we started way back with actinium. Almost universally, when we were thinking about each element, we've started off thinking we probably won't have much to say about it. And by the time we finished, we've had our eyes well and truly opened. Thank you, Allan. This has been a treat, as always.
Yes, it has been quite the ride, hasn't it? I've certainly learned new stuff. I've certainly relearned stuff. I've got to wax lyrical about my favourite subject. And on top of everything, I get a nature chemistry paper out of all of this. So it's absolutely been fantastic. And I have to say thank you so much, Alison, for taking my dry sow's ear of chemical facts and turning them into really rather cool silk purses every episode. So it's Alison who does the hard work on all this one, folks. So thank you so much.
I don't know. I think it's a joint effort.
But whatever, it's hugely appreciated. And it's been fantastic, and I've thoroughly enjoyed it. And I hope all the listeners out there have too. So the entire elemental archive will remain available for perhaps not as long as a zircon crystal, but at the very least a long time, hopefully, at rnz.co.nz/chemistry.
It will also remain available as a podcast out there in that ever-expanding podcast universe. And no, it's never too late to go back and listen to earlier episodes again, or to recommend the series to friends and family. Help the series achieve a little bit of podcast immortality, maybe.
Yeah.
It's been a delight to bring you this podcast series from RNZ. Thank you so much for your company and interest along the way. You certainly made the effort worthwhile. But for now, it's time to bid you farewell. I'm Alison Ballins.
And I'm Allan Blackman. And bye for now. Thanks for your company. And mā te wā.
This is it then.
Yeah, I suppose so.
What are we going to do now?
Oof. I don't know, just go back to our day jobs, I guess.